bivalve mollusk, no bigger than your fingernail, destroyed entire naval fleets from the inside out. Pliny the Elder named it in 77 CE. A very small worm, which the Greeks called Teredo and the Latins Pediculus maris, penetrates ships' timbers. He was riding about rotting hulls in Mediterranean harbors. Nobody listened closely enough. Teredo navalis is not a worm. It has no eyes. The shell, those two tiny ridged plates, faces forward, grinding into wood with a ratcheting motion. The rest of the animal stretches behind it, pale and soft, sealed inside a calcium tube it secretes as it bores deeper. 30 centimeters long, the width of a pencil. Almost nothing to look at. The destruction it causes is something else entirely. In 1730, Dutch harbor inspectors noticed the dike pilings had gone soft. They pulled timber from the water and found it honeycombed. Solid on the outside, almost nothing within. The infestation had been running silently for months. The Netherlands, a country built on controlled water, suddenly faced the possibility that its dikes would simply dissolve. A parliamentary emergency followed. William Wood wrote in 1589 that Teredo has often decided the fate of nations, and may be said to have changed the destiny of the world. He was not exaggerating. In 1588, Spanish Armada vessels showed extensive shipworm damage during the English Channel campaign. Hulls already weakened before the storms hit. The animal does not announce itself. A timber can look sound, barnacled, crusted, ordinary, and be structurally gone. Diver's hand against a piling. The wood crumbles inward. Here is what nobody has fully explained: the biology of how Teredo navalis actually digests wood breaks a fundamental rule of animal digestion. The mechanism lives inside a single organ found nowhere else in the animal kingdom. That organ, and 40 years of research that still cannot account for it, is where this story goes next. Here is the obvious explanation. Teredo navalis bores through wood using its shell plates like a drill. Back and forth rotation. Mechanical abrasion. Case closed. Except it is not closed. The shell plates are smaller than a thumbnail, semi-translucent at the edges. Under magnification, the leading ridges are fine, almost delicate. A marine biologist holding them in forceps under a bench lamp described them in a 2019 University of Portsmouth study led by J. Reuben Shipway as structurally insufficient to explain observed damage rates. Here is the number that breaks the mechanical theory. A single Teredo navalis can bore 30 centimeters of hardwood in a matter of weeks. Not softwood, hardwood. Dense tropical species, the kind shipwrights specifically selected because ordinary wood could not withstand open ocean. The shell plates cannot do that. Not at that speed. Not at that scale. Think about what 30 centimeters of hardwood means. A mechanical drill bit pressed against oak generates heat, resistance, visible friction. It leaves ragged edges. Teredo tunnels are smooth, clean. The boring mechanism accounts for entry, but not what happens after. In 1920, the U.S. Navy established an emergency research program in San Francisco after shipworm damage destroyed pier infrastructure worth millions of dollars. Engineers examined the pilings. The exterior surfaces were intact. The interiors were hollow. The shell plates had created an opening. Something else had done the rest. Ruth Turner noticed this at Harvard in 1966. Her monograph on Teredinidae systematics documented the anatomy in precise detail and flagged an organ nobody had adequately explained. Small, specialized, located inside the animal's body, nowhere near the shell plates. It was not part of the drilling mechanism. So if the shell plates create the tunnel entrance, and the shell plates alone cannot account for the destruction of the wood inside, then something biological is consuming that wood from within. The question is what? Wood is almost indigestible. Not difficult. Almost impossible. Cellulose, the molecule that makes wood rigid, that holds a ship's hull together, is one of the most chemically stable structures in biology. Most animals cannot touch it. Most bacteria cannot touch it. Evolution spent hundreds of millions of years building something essentially indestructible. And Teredo navalis eats it for breakfast. For centuries, nobody understood how. The drilling was mechanical. That much was clear. The shell plates rotated, abraded, bored. But mechanical grinding does not explain digestion. You can shred cellulose all day. You still cannot absorb it. Something else was happening inside that pale, elongated body. Ruth Turner, Harvard Museum of Comparative Zoology, spent years mapping Teredo anatomy. What she found near the digestive tract stopped her. A small, pale organ. No analog in any other bivalve. No precedent in the literature. She named it the gland of Deshays. It should not exist. In 2011, Daniel Distel at Northeastern University sequenced the genome of the bacteria living inside that gland. The species Teredinobacter turneri. The sequencing showed the shipworm's own genome contains no cellulase genes. None. The animal cannot digest cellulose. It never could. Instead, it farms bacteria that can. The gland of Deshays is not a digestive organ. It is an incubator, a controlled colony, a living enzyme factory housed inside a living drill. Without those bacteria, the shipworm starves inside the wood it has already bored. Distel's team confirmed this in laboratory conditions. Remove the bacteria. The animal dies within days. The relationship is not opportunistic. It is not casual. It is total. Neither organism survives without the other. But here is where the story tilts completely. Every adult shipworm carries Teredinobacter turneri. Every one. Yet the larvae, microscopic, drifting in open ocean, nowhere near wood, carry nothing. No bacteria. No gland. No mechanism science has fully mapped. So how does each new generation acquire the exact colony it needs to survive? Here is the payoff. Teredo navalis cannot digest wood. Not slowly. Not inefficiently. Not at all. The animal that hollowed entire fleets, that nearly drowned the Netherlands in 1730, does not possess a single enzyme capable of breaking down cellulose. So how does it eat? Inside the shipworm's body sits an organ called the gland of Deshays. It exists in no other animal on Earth. Not a variation of something else. Not a modified structure borrowed from a distant relative. Nothing like it has been found anywhere in the animal kingdom. Inside that gland lives a colony of bacteria, Teredinobacter ternary, and those bacteria do what the shipworm's own genome cannot. They produce cellulase enzymes that break cellulose into usable sugars. The shipworm does not digest wood. It farms the bacteria that digest wood for it. In 2011, Daniel Distel at Northeastern University's Ocean Genome Legacy Center published the first complete genome sequence of Teredinobacter ternary in PLOS I. What he found confirmed what Ruth Turner had begun mapping at Harvard in 1966. The symbiosis is not optional. Remove the bacteria in laboratory conditions, and the shipworm starves inside the wood, surrounded by food it cannot touch. But here is what 40 years of research still cannot answer. A Teredo larva hatches free swimming, in open ocean, carrying no bacteria. Somehow, before it ever contacts wood, it acquires the exact right bacterial strain. The mechanism remains unmapped. No confirmed pathway, no reliable protocol to replicate it outside the host. Teredinobacter ternary cannot be cultured consistently in a laboratory dish. The binders documenting failed attempts fill entire shelves. The global shipping and harbor industry spends an estimated $1 billion annually on antifouling coatings, copper sheathing, and concrete replacement, all to stop an animal the length of a pencil whose core biology science cannot fully replicate. A pencil-sized mollusk, an organ found nowhere else. A bacterial partnership no laboratory has successfully reproduced. The gland of Deshays is filed here, under mechanisms that should not exist, in an animal that should not work. The deep index stays open. Subscribe for a new breakdown like this every day.